Hi, welcome to the Unit 2.1a Solutions Chemistry video. So in this video, we're focusing on key question 2, which is how do we describe qualitatively and quantitatively what happens during dissolution. This video is broken down into 2 parts, and this is part 1. So in this unit, we're going to be looking at 2 main types of chemical reactions that occur in solution: precipitate reactions and neutralization reactions. And you've heard of precipitate before. And neutralization is when you combine acids and bases together to sort of neutralize one another. All right, so all the reactions and then also a physical change we'll be looking at, they all occur in solutions. And this is just a recap of some solutions terminology. So remember, a solution is something that's a homogeneous mixture of 2 or more substances. And what that means is that it looks the same if you're seeing it with your eye or under a microscope. Example of that would be this Gatorade or saline solution. Non-examples of solutions would be something like Italian dressing. You can clearly see the oil and then the more watery parts and little bits in there, so you can see that they're different pieces. 2 other things that are not solutions are blood and milk. Even though they look the same with your eye, if you look at it under a microscope, you can see the red blood cells and the white blood cells. For milk, you can see like sort of these fat and protein globules. So these are not solutions. Just a quick note that there are, we typically think about things that involve solids and liquids together that are solutions, but there are other types. You can have solids as an alloy like brass. Air is a solution of gases, and there's oxygen that's dissolved in water, like oceans and lakes, and that's how the fishes breathe. So that would also be an example of a solution, in this case made from a liquid and a gas. So these are all examples of solutions, even though they don't involve liquids and solids, but in this unit we focus mainly on liquids and solids. All right, so parts of solution terminology. Remember, solute is the stuff that gets dissolved, and solvent is the stuff that does the dissolving. So an example of that would be like making a Kool-Aid solution. The Kool-Aid is your solute, and you're going to add it to the solvent, which is water, and together they make the Kool-Aid drink, which is your solution. So we're now going to start utilizing phase notations throughout this unit, sort of to like keep track of what phase that we're in. So that's super important. So if we were doing this with this Kool-Aid example, the Kool-Aid, we would give it a solid, an S for solid. The water, we would give it a liquid, because H2O is a liquid. And then for the solution itself, we use this phase here, AQ, which stands for aqueous. So whenever you see aqueous, that means it's something dissolved in water. So you need to start getting used to utilizing these phases, and the phases are usually written in parentheses to the right of whatever the species is that the phase is referring to. Okay, so let's do a quick CFU. You're going to identify the parts of the solution here. We have sugar, water, and this is the chemical formula for table sugar. So you have sugar being dissolved in water, and here you have a sodium hydroxide solution. For each of these, you identify the solute, solvent, and solution, and be sure to utilize the phases. Pause the video now. When you press play again, the answer will be revealed. Okay, so we have our solutes, solvents, and solutions here, so you can take a look at it. Make sure for the solutes, in both cases, this should be solid. I guess I should have mentioned that, by the way. Sodium hydroxide is it is a solid. It's a salt, so it's a solid. Water is our solvent for both cases, and that's a liquid. And then for both solutions, we use this AQ phase to represent the solution. Okay. So now that we've done a recap, before we dive any further, like you may be asking, why is this even important? Okay, so as you know, most of the Earth is covered in water. Our bodies are made up of mostly water. So that means that there's a lot of natural and biological processes that involve chemical reactions that occur in solution. And so some of the terminologies that we use, and also a lot of our understanding of chemistry takes place in or involves these types of reactions. And so that's why we are learning about them. All right, so I've already mentioned the two types of chemical reactions, acid-base and precipitation reactions, but there's also, in addition to a chemical reaction, there's a physical change that we also look at when we're talking about solution, and that's dissolution. And that's when we dissolve something in water. So that's what we're going to focus on for the 2.1 note videos. So let's take a look at what happens when stuff dissolves in water. As you probably remember, when you have something like salt, which is an electrolyte, it ionizes, means it breaks apart into its ions. And an ion is anything with a charge, whether it's a plus charge or a minus charge. And so we have an image of that here. We can see this, this is like a salt, like sodium chloride. And when it's a solid, it's in this lattice network here. So all the cations and anions are together. Once you dissolve it in water, it breaks apart into those two different types of ions. So you have your anions surrounded by waters and your cations surrounded by waters. On the other hand, non-electrolytes, they break down into smaller pieces, but they do not dissociate into ions, meaning they don't break apart into ions. So if this was sugar, this would still be a sugar molecule. It's just that they're not all the sugar molecules are not all clumped together. They're just sort of spread out throughout the water. Okay, so you can kind of tell from that depending on what you have, things can dissolve differently. And for ionic compounds like salts and also bases, we'll be looking at that in a moment, when they dissolve, they do form ions, so they would be considered electrolytes. Acids also break apart into ions, so they would be considered electrolytes. And acids would fall under molecular covalent molecules. There are also things called molecular bases, which we'll look at later, and polar molecules. These two things don't break apart into ions, but the molecular bases will form ions, and we'll see where those ions come from, but the molecular base itself doesn't break apart into, like, let's say, N-3 and H plus 1 ions. Okay. So what happens, let's look at what happens when we dissolve a salt in water, and then later we'll look at what happens when we dissolve acids and bases in water. So a couple of key things. Ionic compounds have a positive and negative part, as you know, they're anions and cations. And when you dissolve it in water, it breaks apart into those things. So how do you figure that out? What you need to do is you need to be able to determine the number of cations and anions using the subscripts and the charges of the cations and anions to show what happens when the salt breaks apart. And for the charges, we can use common charges, our understanding of polyatomic ion charges, and for transition metals, we have to figure it out. This is sort of the same skills that you use when you were naming ionic compounds, so a lot of this will not be new to you. Here's just a quick image of the common charges. We will be utilizing our understanding of this, so it's useful to have. And what I mean by common charges, remember group 1s have a +1 charge typically, group 2 +2 charges, group 13 +3, group 14 plus or minus 4, group 15 -3, etc. And in the middle here we have our transition metals, and they have all sorts of charges, so whenever we're dealing with them we have to figure it out. All right, here are some example problems. What we're going to do is we're going to our aim is to be able to write down the chemical equation when we dissolve these 3 salts in water. So let's begin by figuring out what ions they're going to form when you dissolve them in water and how many of each of those ions are going to form. To do that, let's start with our first example, potassium sulfite. We're going to split it apart into the cation side and anion side, or the metal side and the non-metal side. And then we're going to sort of break it into its ions. So we know that potassium is in group 1, so it's going to have a +1 charge. And there are 2 potassiums, so we're going to have 2 of them. And I know that there are 2 potassiums because the subscript here is 2. So I'm going to write this as 2 Ki plus. 2 because I have 2 potassiums, and the charge is +1 because potassium is group 1. Then that leaves me with my anion here. Sulfite has a -2 charge, and there's only 1 of them. So for my anion, I write it as SO3 2-. Let's look at another example for copper. So first thing I'm going to have you guys do on your own is I want you to sort of split it up into the cation and anion part. Okay, great. So the line would go between the copper and then the nitrate. Now we're going to break this down into its cations and anions. For copper, there's only one of them, but copper is a transition metal, so we don't know the charge. So I'm just going to put a question mark here currently, and then we'll change that later once I know the charge. The polyatomic ion is nitrate, and there are two of them. And I know that there are two because in this case, you'll see that the 2 is outside of a parentheses. So whenever we have more than one polyatomic ion, we always put a parentheses around it and then the subscript to tell us how many we have. This subscript on the inside, the 3, that goes with the polyatomic ion. It doesn't tell us how many of them that we have. So anyway, there are 2 of them and then it has a -1 charge. I'm going to use the charges from the anion side to figure out the charge on the cation. So remember that the overall charge here must be 0. So then from the cation side, since I have 2 nitrates, 2 times -1 will give me a -2. So on this side I have a -2 charge. And since I only have 1 copper, that means that the charge on this copper must be +2 in order so that these 2 charges cancel out. All right, we're going to do the same thing with Fe3 and 2. Why don't you give it a go, and then when you press play, we'll see how we do it. All right, so we split it up, and we have 3 irons and 2 nitrides. And because nitrogen's in group 13, it has a 3- charge. So then we need to figure out the charge on the iron. We have 2 of them, 2 nitrides, so 2 times -3 gives us the overall -6 charge on the anion side. That means for the cation side, since I have 3 irons, 3 times whatever the charges of that should be +6. And so doing some mental math, I know the charge of the iron is going to be +2. All right, so now that we have our charges here, we're going to use this information to write our chemical equation. So to write the chemical equation, it's real simple. Let's take a look at it for potassium sulfite. What we're going to do is we're going to start with our salt, that's our reactant, and then these 2 become our product. And then we also have to consider the phases. The salt or the ionic compound is going to be a solid phase, and then these 2 will be aqueous. And so that's what we did here. K2SO3 solid, broken apart into its 2 ions, and we use aqueous phases for those. All right, I want you to try it for these 2, for the copper nitrate and the nitrate, and then the iron nitride. And when you press play again, the answer will be revealed. Okay, so here we go for the copper to nitrate, it should look like this. And for the iron to nitride, it should look like that. All right, so now that we've seen what it looks like, it's your turn to write the chemical equation that shows the dissolution of these 3 salts, and you're going to write your chemical equation here. You're going to do the same work that we did, sort of split it up and figure out the number of cations and anions and the charges on the cations and anions. And then you're going to translate that information into a chemical equation. Don't forget to utilize the solid and aqueous phases appropriately. All right, pause the video now. When you press play again, the answer will be revealed. Great, so here are the answers. Check your work. If you have any mistakes or have any questions, please be prepared to bring that to class. All right, finally, our last CFU, you've sort of seen this problem before, so take a moment to sort of tackle it, but now you have a better understanding because you've seen how salts break apart in water. All right, the answer for this is C, and that's because when the ammonium sulfide dissolves in water, the subscript here too is telling us that we'll get double the amount of ammoniums, and so that means the concentration itself will be doubled. And that means that the number, since this gives us the greatest concentration, that means it'll have the highest concentration of NH4+. All right, we're going to move on to part 2. So you're going to pause this video, and or you're going to stop this video, and then you'll watch part 2.